Sound is all around us, but some of our most common, everyday noises can reveal amazing secrets about physics. Welcome to our highly tuned and specialized test setup. An anechoic chamber designed to absorb all echoes. This means we'll only hear the direct sound of the impact and no reflections. Our level 2 sound meter captures decibel readings across the full frequency range of human hearing. Our shotgun mic captures clean audio signal. The sound camera pinpoints visually exactly where the sound originates. And the iPhone is used to record slow motion footage so we can see and hear the moment of impact in incredible detail. Sound is the result of oscillations that propagate in a medium, much like waves in a body of water. These waves create high and low density regions that are referred to as compression and rarefaction. The frequency, measured in cycles per second, or hertz, of these waves determine the pitch of the sound. The greater the frequency, the higher the pitch. We have broken down the frequency range of human hearing into 7 different frequency bands to better convey how that frequency band is perceived. You are now seeing the ambient noise level of our anechoic chamber overlaid on this graph. This ambient noise could be contributions from a myriad of sources, like the ground hum of electrical power, HVAC units, and many more. Let's explore the sound of a deck of cards being shuffled. On the left-hand side, we see our sound cam footage. Notice the bright red spot at the center where the cards meet. Below that, in real time, we see the spectra. Now let's take a closer look at the graph. Notice the frequencies between 20 and 50 Hertz. This is more than likely the result of air directly impacting the microphone. We have a slight bump in the boom, and then everything above that signifies that light, airy sound of a shuffle. Now let's take a look at snapping our fingers. Once again, we can see the sound cam on the left identifying the loudest portion of the noise. Let's look at the graph once again. Take a look at the plateau in the wisp and air region. This region, found in the human voice, holds the frequencies in the human voice that creates consonants. Take your fingers and rub them together close to your ear. Those are the frequencies in question. Now let's take a look at a lighter being struck. Due to the sensitivity of the sound cam, we chose not to get it close to an open flame. Instead, let's take a look at the graph. Notice the lack of lower and mid-range frequencies. The flint against steel of this mechanism creating the spark mostly generates higher frequencies. Now we see a comparison of all 3 sounds we captured. We see the low-end rumble generated by the air being pushed out of the card shuffle, the plateau between 2 kHz and 8 kHz of a snap, the result of the texture of our skin, and the prominence of the higher frequencies in the lighter being struck due to the flint and steel. We look forward to sharing more of our signal archive in the future. Thanks for joining us.